Hello students, welcome to this lecture on Introduction to Three-Dimensional Geometry. In this lecture, we will cover NCERT sections 11.1 to 11.3. So let's get started. This is a disclaimer. In today's lesson, first we discuss introduction of this chapter. After that, we discuss coordinate axis and coordinate planes in three-dimensional space. Then we discuss coordinates of a point in space. So finally, we discuss the key concept covered in this chapter. So I hope you are with your notebooks and pens ready. So now let's start first topic 11.1 introduction. So let's start by thinking about two-dimensional geometry. Imagine two straight lines crossing each other at a perfect right angle, just like the corner of a square. So this is the basic setup we use to describe positions on a flat surface. Now let's examine these two lines more closely. One of them runs left to right, which we call the x-axis, and the other goes up down the the axis. That axis is called y-axis. Okay, so these axes help us describe any point in a flat plane. Notice how in three-dimensional geometry we add one more line, just like in 2D. So we want all the lines to cross each other at perfect right angles or 90 degrees. So this gives us three axes instead of just two. So let's look at what these three axes represent. One still goes left to right, another goes forward and backward, and the last one goes up down. Okay, so this setup allows us to describe position in space, not just on a flat surface. Okay, so in 3D we describe position of a point in space. Okay, not just on a flat surface. So this shows us how useful three-dimensional geometry is. So we can describe the position of objects like a fan in a room, a satellite in orbit, or even a molecule in a crystal lattice. Okay, all of these need three coordinates to show exactly where they are. Finally, let's examine how we specify a location in 3D space. So we do this by measuring the perpendicular distances from the object to each of the three walls or planes that meet at right angles or 90 degrees. Okay, so this method gives us a clear and precise way to describe any point in space. Now let's start by looking at this diagram. Here we see three different planes all meeting at a single point, which is labeled as O. Okay, so these planes are arranged so that each one is at a right angle to the other two. Okay, so this setup is the foundation of understanding three-dimensional geometry. Okay, so here we consider three planes intersecting at a point O such that these planes are mutually perpendicular to each other. Okay, and this is shown in figure 11.1. So very carefully look at figure 11.1. Okay, and try to understand how these three planes intersecting at a point O. Okay, and then try to understand how we can find position of a point in this space. So now let's examine these three planes more closely. Okay, so we call them the coordinate planes because they help us describe the position of points in space using coordinates. Okay, so each plane represents a flat surface where two of the three axes lie. Okay, now notice how the planes intersect along straight lines. So these lines where the planes cross are called the coordinate axes. Okay, so they are the main reference lines we use to measure positions in three dimensions. The first line is labeled as x dash ox. Okay, and we call this the x axis. This axis runs horizontally in the diagram and is used to measure how far a point is along the x direction. Okay, the next line is y dash oy, which is the y axis. Okay, so this axis runs perpendicular to the x axis and helps us measure how far a point is along the y direction. The third line is z dash oz, which is the z axis. This axis is perpendicular to both the x axis and y axis, and it measures how far a point is above or below the other two axes. Finally, the point where all three axes meet is called the origin. And what is the coordinate of the origin? The coordinates of the origin are 0, 0, 0. Okay, and it serves as the starting point for measuring positions in three-dimensional space. Here we see an introduction to the three coordinates planes in three-dimensional geometry. So take a look at figure A, which shows the three axes x, y and z. Okay, and while meeting at the origin, the coordinates of origin are 0, 0, 0. Okay, so this diagram will help us understand how points and planes are positioned in 3D space. So very carefully look at this diagram. Now let's examine the first coordinate plane called the xy plane. So this plane contains both the x-axis and the y-axis. Okay, so imagine it as a flat surface that stretches out left, right, and forward, backward. Okay, but has no height. Now notice how we have the YZ plane. Okay, so this plane contains the y-axis and the z-axis. So think of it as a vertical wall that goes up, down and forward, backward, but has no width along the x-axis. Next, we have the XZ plane. This plane contains the x-axis and the z-axis. So you can picture it as a vertical surface that goes left to right and up and down, but has no depth along the y-axis. So the three axes x, y and z are arranged in what we call a right-handed rectangular coordinate system. So this means if you point your right hand's thumb, index and middle finger along the x, y and z axis, they will point in the positive directions and form a right angle with each other. This 3D coordinate system shows both the positive and negative directions for the x, y and z axis. So all meeting at the origin, which we label as O. The coordinates of origin O are 0, 0, 0. Okay, so understanding these directions is important for locating any point in three dimensional space. Now, let's start by thinking about how three-dimensional space is organized. Okay, in two dimensions, we have the x and y axis dividing the plane into four coordinates. So in three dimensions, we add another axis, the z axis, and this creates a more complex division of space. So let's examine what happens when we introduce the three coordinates planes, the xy plane, the yz plane, and zx plane. Okay, so these planes intersect and divide the entire space into 8 distinct regions, which we call octants. Okay, so you can see this illustrated in figure B on the slide. So notice how the position of a point in space depends on the signs of its coordinates x, y, and z. Okay, so the combination of positive and negative values for these coordinates tells us exactly which octant the point is located in. So here the signs of the coordinates x, y, z of a point determine the octant in which the point lies. So this shows us a convenient way to represent the octants using the signs of the coordinates. For example, the first octant is where x, y, and z are all positive, written as plus, comma, plus, comma, plus. The other octants follow different combinations of plus and minus signs. Okay, as listed here. For second octant, it is minus, comma, plus, comma, plus. For third octant, it is minus, comma, minus, comma, plus. Okay, and for fourth octant, plus, comma, minus, comma, plus. For sixth octant, minus, comma, plus, comma, minus. For seventh octant, minus, comma, minus, comma, minus. Okay, for eighth octant, plus, comma, minus, comma, minus. So now let's keep in mind an important remark. There is no universal agreement for numbering. Okay, octants 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so different textbooks or sources might use different numbering systems for the octants. However, the important thing is that the signs of the coordinates for each octant are always defined in the same way, no matter how the octants are numbered. Okay, so the sign pattern for x, y, and z in each region stays consistent. Here we see a point P in three-dimensional space, and its coordinates are labeled as x, y, and z. Okay, so these coordinates represent the perpendicular distances from a point P to each of the three coordinate planes. Okay, so take a look at the diagram. Notice how P is positioned in relation to the axis and the planes. So this is the basic idea behind locating any point in 3D geometry. So now let's examine the x coordinate first. The x coordinate tells us how far point P is from the yz plane, measured along a line perpendicular to that plane. So if we imagine dropping a straight line from P to the yz plane, the length of that line is the x coordinate. Now notice how the y coordinate works. The y coordinate is the perpendicular distance from point P to the xz plane, just like before. So if we draw a straight line from P directly to the xz plane, the length of that line gives you the y coordinate. Finally, let's look at the z coordinate. So this shows us the perpendicular distance from point P to the xy plane. So if you draw a line straight down from P to the xy plane, the length of the line is the z coordinate. So this way, all three coordinates together tells us exactly where P is in space. Here we see a diagram labeled as figure 11.2, which will help us understand how to describe the position of a point in three-dimensional space. Okay, so before we reveal any steps, just take a moment to look at the picture and notice the different lines and points. Okay, so this diagram is the foundation for understanding coordinates in 3D geometry. So from point P, we drop a perpendicular PM to the XY plane, and we call the point where it meets the plane as M. Okay, so this means that M is directly below P, lying flat on the XY plane. Now, from point M, we draw another line, this time perpendicular to the x-axis. Okay, so this new line meets the x-axis at a point we will call L. Notice how we are breaking down the position of P step by step. So first vertically, then horizontally. The distance from the origin O to the point L along the x-axis is what we call the x-coordinate of point P. So this shows us how far along the x-axis the point P is. So if we ignore its height and depth for now. Next, the distance from L to M moving parallel to the y-axis gives us the y-coordinate. This tells us how far P is from the x-axis in the y direction. Again, just considering the flat xy plane. The length of the perpendicular from M up to P, which is the line MP. Okay, so it represents the z coordinate. So this shows us how high above the xy plane and the point P is located. So by combining these three distances, OL for x, LM for y, and MP for z, we can describe the exact position of P in space using the coordinates x, y, z. So this is the basic idea behind three-dimensional coordinates. Now let's examine this diagram of a point P with coordinates x, y, and z. Okay, inside a rectangular box or cuboid. So the box is formed by planes that are parallel to the x, y, and z axis. Okay. Notice that how three planes, each parallel to one of the coordinate planes, so will meet at the point P. So these planes help us define exactly where P is inside the cuboid. Okay. So this shows us that P is determined by its distances from the three axes. So these planes will also intersect the x-axis, y-axis, and z-axis at specific points, which are labeled as A, B, and C. So point A is where the plane meets the x-axis, B is on the y-axis, and C is on the z-axis. If we let OA equal x, OB equal y, and OC equal z, then the coordinates of point P are simply x, y, z. Here we see a diagram labeled as figure 11.3, which helps us visualize points in three-dimensional space. So notice that three axes x, y, and z. Okay, so this is the foundation for understanding how we locate points in 3D geometry. So before we reveal more, let's focus on how these axes work together to define our position. So let's examine what happens when we are given coordinates like x, y, z. Okay, so these numbers tell us exactly where a point is located in three dimensional space. Okay, so our goal is to use these coordinates to find the position of a point, which we will call P. So now notice how we start by locating points A, B, and C on the X, Y, and Z axis. So point A is at X, 0, 0. Point B is at 0, Y, 0. And point C is at 0, 0, Z. Okay. So these points help us set up the location of P by marking its distances from each axis. Now let's draw planes through these points. Each plane is parallel to one of the coordinate planes. The YZ plane, ZX plane, and XY plane. Okay, so this shows us how we use these planes to narrow down the exact position of point P in space. These three planes intersect at a single point, which is our point P. Okay, so this intersection is important because it confirms that the coordinates x, y, z uniquely determine a point in three-dimensional space. So by using the axes and planes, we can always find the location of any point. Finally, let's look at the distances. So point P's perpendicular distances from the YZ plane, ZX plane, and XY plane are X, Y, and Z respectively. So this means that the coordinates directly tells us how far P is from each of these planes, making it easy to visualize and locate points in 3D geometry. Now let's look at this example. So in the diagram, point P has coordinates 2, 4, 5. The question asks us to find the coordinates of point F. So take a moment to observe the figure and think about how the coordinates of F might relate to those of P. Okay. So let's start the solution of this example step by step. So for the point F, the distance measured along OY is 0. Therefore, the coordinates of F are 2, 0, 5. So this shows us that when a point lies directly above or below the XZ plane, its Y coordinate is 0. Okay, and the other coordinates stay unchanged. So I hope this example is clear to all of you. This was very simple example. Okay. So now let us see another example. So in this example, we have to find the octant in which the points -3, 1, 2 and -3, 1, -2 lie. Okay. So first of all, think about the signs of the x, y, and z coordinates for each point. Okay, and recall how octants are determined in three-dimensional geometry. So now we will discuss its solution. So first of all, let's see what we have given. Okay, so we have given that the points -3, 1, 2 and -3, 1, -2. Okay, and our goal is to figure out which octant each of these points belongs to based on their x, y, and z coordinates. So we know that from 8 octant system in 3D, which we can be represented as first octant plus, 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 second octant minus, plus, plus, third octant minus, plus, for fourth octant plus, minus, plus, okay, for fifth octant plus, plus, minus, okay, and for sixth octant minus, plus, minus, for seventh octant minus, minus, for eighth octant plus, minus, okay. So this shows that the point -3, 1, 2 lies in second octant, and the point -3, 1, -2 lies in octant 6. So I hope this example is clear to all of you. Now we will examine the question. Here we are given 4 points in 3-dimensional space, and we need to identify which octant each point lies in based on their x, y and z coordinates. Okay, so first of all, take a moment to look at each point and think about which octant it might belong to. Here we have a question asking us to identify the octants in which certain points lie. Okay, based on a given octant system. So let's start the solution step by step. So using the provided octant system, the signs of x, y and z in different octants as follows. For first octant, plus, plus, plus. For second octant, minus, plus, plus. For third octant, minus, plus. For fourth octant, plus, plus. For fifth octant, plus, minus. For sixth octant, minus, plus, minus. For seventh octant, minus, minus. And for eighth octant, plus, minus. Now let's examine point A, which is 1, 2, 3. All three coordinates are positive. X is positive, y is positive and z is positive. So what we can say for point 1, 2, 3. So therefore the point is on the first octant. Next, let's look at point B, which is -4, 2, 5. Here x is negative, y is positive and z is negative. Okay, so what we can say, so for the point -4, 2, 5, the x coordinate is negative, the y coordinate is positive and the z coordinate is negative. Okay, that means minus, plus, minus. So therefore this point is in the sixth octant. Now let's consider point C, which is 2, -1, 3. Here x is positive, y is negative and z is positive. Therefore, this point is in the fourth octant. Finally, let's look at point D, which is -3, -1, 6. In this case, x is negative, y is negative and z is positive. Okay. Therefore, the point is in the third octant. Now, let's look at another question. In this question, we first let P be the point 3, 4, 5, and then we have to find the coordinates of the feet of the perpendicular drawn from P to the following coordinate plane. Okay, the first coordinate plane is the xy plane. The second coordinate plane is the yz plane. The third coordinate plane is the xz plane. Okay, so first of all, think about how the coordinates will change for each case. Okay. So let's start the solution of this question. So given that the point P 3, 4, 5, when a perpendicular is drawn from a point to the xy plane, the z coordinate becomes 0. Okay. Thus, the foot of the perpendicular from point P to the xy plane has coordinates 3, 4, 0. Now moving on to the part B, for yz plane, we need to set the x coordinate is 0. Okay, so the yz plane is made up of all points where x is 0. So this shows us the foot of the perpendicular from point P to the yz plane will keep the y and z value the same, but the x value becomes 0. So the coordinates are 0, 4, 5. Now, let's consider part C. For the xz plane, we said the y coordinate is 0. Okay, so the xz plane contains all points where y is 0. Therefore, the foot of the perpendicular from point P to the xz plane will have the same x and z values as P, but the y value will be 0. So, the coordinates are 3, 0, 5. So, thank you for your attention. I hope this lesson was helpful to all of you.